And yeah, so we've got 3 talks today across very different time zones, hence why the event is so spread out, more spread out than usual. But yeah, so we'll begin with our first talk by Disheng Xu from Great Bay University, who'll be speaking on the dimension theory of random walks and group actions by circle diffeomorphisms. Over to you, Disheng.
Thank you, and thanks for the invitation. And so today we talk about fractals, and especially about fractal sets from random walks and group actions by circle diffeomorphism. Is it okay now? Sorry.
Yeah, someone just tapped their mic.
It's okay. Yeah, we can see it.
Yeah, okay. Then yeah, let me start. Yeah, okay. So this is a joint work with Disheng Xu and Weikun He. And by the way, I think Weikun gave a talk like last week at Imperial College. So if someone from there, so I'm sorry. So maybe almost the same, the talk. Yeah. Okay. So we start from fractals. Okay. Oh, yeah. So basically, we both interested in 2 classes of fractals, I think. So from a dynamical view, people either interested in IFS, so it's the limit set of attractors defined by semi-group actions, and the other one is the limit set of attractors of actions by groups. So it's either semi-groups of groups. So I think there are like maybe the main examples of fractal sets. Okay. And so we wonder how to characterize the size of fractal sets, and people use dimensions to characterize it, actually. And then let's start from Hausdorff dimension, but I believe all of you are experts and more familiar with it than me, so just skip it maybe. So this is dimension. So this is definition for the outer measure, and then we can define the Hausdorff dimension for arbitrary set. Just take the critical S as the Hausdorff dimension of the set. Okay. And now let's see some examples. So we just talk about the IFS. So you can see here the Cauchy snowflakes are actually linear IFS, means that when you define the semi-group actions, they are using linear maps and then also conformal linear maps. So I call it conformal linear IFS. And the middle one is the rosy gasket. It's still defined in as a limit set of semi-group actions, and then but each element is non-conformal, and then it's by projective transformations. And the right-hand side one is the limit set of group actions. And so it's a limit set of Kleinian groups. So that's why I said conformal group actions. So the element is conformally acting on the set. Yeah, okay. And let's come back to the most famous one, the 1/3 Cantor set. And it can be defined by IFS. I think it's well known. So 2 maps, one is the x to x over 3, and the second one is the x to x plus 2 over 3. Then the Cantor set can be defined as a attractor of this semi-group generated by F0 and F1. So we call it lambda third. And this is the picture. And here we want to emphasize that actually the Cantor set, so once the Cantor set is the unique minimal closed subset of the semi-group actions. And it's well known that the Hausdorff dimension of the Cantor set is log 2 over log 3. I think we will get it back later. Okay. And today we will talk about the limit set of group actions on circle. So you can see here the Cantor set can be defined as the minimal closed subset, invariant subset of semi-group action. So we can define the limit set for group action similarly in the following way. So this is a very general definition, and then actually it's coming from a theorem. So we take a group of circle homeomorphisms, and then so for convenience we assume them they preserve the orientation, and then we take an arbitrary subgroup of it. Then we have a dichotomy. So not dichotomy. We have a classification of the closed orbit. So either G has a finite orbit, or every G orbit is dense, means that the only one closed orbit of G is the whole S1. And then the third one, we really see the counter. Oh, sorry, we really see the fractal set. So G has a unique minimal closed invariant set, which is homeomorphic to a counter set. This is the fractal set we are interested in. And this set is actually is contained in a set of accumulation points for every orbit. So you can see this one is really a limit set. And you can see the first one, the orbit is not so interested, it's finite orbit. And the second one, the closed orbit is the whole manifold. So we are interested in the third one. This is really the fractal set. And the people call the third case saying that G preserving an exceptional minimal set. So this is we couldn't find actually who proved this theorem, but we can see this theorem from some textbook. So maybe it's even dated back to Ray, I guess. Yeah. Okay. So the famous example for this theorem is the Fuchsian group actions. So we consider a Fuchsian group means that it's a discrete subgroup of KCl2R, and it's isometrically acting on the boundary disk, and then induces an action on the boundary by projective transformations. So it's a group action on S1, yeah. And if it is not virtually cyclic, so people call it not elementary, then you can see you can prove that gamma preserves a limit set on S1. And if gamma is called the first kind, means that the limit set is whole circle. So it's corresponding to the second case of the last theorem. So last theorem, if you remember, we have three cases. One is G preserving finite orbit, so it's like the virtually cyclic case. And the second case is every G orbit is dense, so it's the first kind case. And then the third case is gamma is called second kind, if the limit set is a counter set. So it's just the exceptional minimal set, actually. Yeah, this limit set is the exceptional minimal set defined in just last theorem. Yeah. So far our classical results. And now we state we state a result in 1970s. So it's by, I think, first proof by Bearden and then Patton Sullivan. So it's on 1970s. So it's not quite recent, sorry. So assume that gamma is a finitely generated second kind of Fuchsian group. So it means that the limit set is a fractal set. And then if the limit set we call lambda, then we have this result. So first is that the Hausdorff dimension of the critical set equals to the critical exponent. So we use delta gamma. And second, the critical exponent is in 0, 1, this interval. So in particular, the dimension of lambda is in 0, 1, this open interval. And the third proposition is that if gamma has a parabolic element, then delta gamma greater than half, means that the limit set has Hausdorff dimension greater than half. And the critical exponent of gamma it's very classical. It's defined as the critical value of Poincare series. And so here the distance is the hyperbolic distance, and O is just point, and then here we take the sum and then let G run over the whole Fuchsian group. And just by some elementary calculation, I mean, through the hyperbolic distance, you can see the delta gamma is actually the limit sup here, the 1 over n, yeah, 1 over n g in gamma, and then the norm, so this set, yeah. And this is a very classical result. And I think at the very beginning, Bearden at least know the first two. Sorry, maybe not. Sorry, the Bearden at least know the second one, and then he proved it by automorphic forms, I think. And then Patterson-Sullivan proved maybe all the three using the Patterson-Sullivan theory or using the Patterson-Sullivan measures. So I think Bearden is slightly earlier, it's at 1960s, and then Patterson-Sullivan is around 1970s. I hope I give correct credits. Okay, and now we can state our main theorem already. So this is a joint work with Yuxiang and Wei Kun. It's on arXiv this year. So we take G as a finitely generated subgroup, but here we do not assume it's fluxing group, just some real analytic diffeomorphism acting on S1. In particular, the fluxing group is an example of our result. And then with an exceptional minimal set, so it's like the second kind for fluxing group. Then we basically show almost the same results as the Bearden Patterson-Sullivan, but we consider the more general group actions. So the first one, we have the dimension is less than 1 and greater than 0. And the second one, we define a critical exponent. We call dynamically critical exponent. And then we get a Hausdorff dimension of the limit set equals to the critical exponent. And the third one is that if G contains an element with a fixed point with a multiplicity k plus 1 in the limit set, then we get a Hausdorff dimension of the limit set greater than k over k plus 1. So if you take k equals to 1, and then if you forget the assumption that in lambda, you will see the third one is the generalization of the Patterson-Sullivan, so Bearden Patterson-Sullivan. And then unfortunately here, the in lambda, this condition it cannot be avoided. We can find counterexample. So here the in lambda, this condition is necessary. Okay, so you can think we basically generalize the result to a more flexible setting because our action there's no hyperbolic distance, no linear structure at all. So it's just diffeomorphism acting on S1. But we need a regularity assumption is that every element is real analytic acting on S1. Okay. And then it can be checked that the dynamical critical exponent we define here is the same. If we consider the fluxing group actions, we can check there the critical exponent is the same as our critical exponent here. The reason is that maybe we can come back to last page. Is here the square of the norm of G actually have certain dynamical meaning. It's correlated to the contracting speed for the projective action induced by G acting on S1. So that's why, so we can compare this limit soup with here this local contracting speed is at least related. You can see here. So that's our main result actually. Yeah. So I hope there's no problem. So I think the statement is, I hope it is clear. Yeah. Okay, and we can also compare our result with another conjecture by Disheng and Sullivan. So the problem is, I think it's coming from people studying codimension 1 foliation in geometry. So Disheng and Sullivan gives a conjecture about the groups acting on circle, but they only consider C2 actions. And you can see this is a conjecture by Disheng and Sullivan. So if G is a finitely generated subgroup of C2, orientation preserving and preserving an exceptional minimal set, so the fractal set, then the Lebesgue measure of of this minimal set is 0. So you may be interested in why they propose this conjecture. So if this conjecture is correct, so it's related to some even more difficult conjecture for the study of codimension 1 correlation theory, saying that if you have a codimension 1 correlation on a compared manifold, and then you take one leaf, you take it out, and then you take the closure. If we can prove a stronger version of D-Sullivan, so maybe they call it Hector D-Sullivan conjecture, the more stronger one. Then you can show the closure of the leaf is either full measure. So the closure of the leaf is either the whole set, or the closure of the leaf has 0 Lebesgue measure on the whole manifold. So I think that is a very natural problem, at least for people studying the behavior of codimension 1 theory, codimension 1 correlation theory. Sorry. And this conjecture is widely open until 2018. So there's a partial result, is a breakthrough by Disheng Xu and Navas. They show that, okay, if we weaken we show we weaken assumption, we assume the G is contained in a real analytic, a group of real analytic diffeomorphisms. Then they really show the conjecture by Disheng Xu. They show the number has Lebesgue measure 0. And in particular, our result this year strengthened not only generalized the classical result by Bearden, Patterson, Sullivan to nonlinear setting. We also strengthened the Disheng Xu and Navas from the Lebesgue measure 0 to cost of dimension less than 1. Yeah. So that's what we prove. I mean, yeah, part of what we proved. Yeah. I think I have like 10 minutes, but maybe I spend like 3 to 5 minutes to say some key ingredients of our proof, and then maybe leave 5 minutes for you if you have questions. Yeah. So the key ingredients of the proof, the first step. So if you familiar with the random walks on homogeneous space or random walks on homogeneous space or random products of matrices. So sometimes people need to consider the Furstenberg boundary map. I think this Furstenberg boundary map also have the analog in the theory of IFS. But in general, if you only consider random walks by circle diffeomorphisms, a priori you don't know how to define the Furstenberg boundary map. This one is very useful in the study of random walks on homogeneous space. So the first step for us is we really generalize the Furstenberg boundary map to our setting. It's no longer it's actually a set valued map, but the lucky thing is that our set value, the set is a finite set. So it's a finite set value map. So we can still define certain Furstenberg boundary map. And then the lucky thing is that this map has many symmetries. So here I write rotation symmetry and time reverse symmetry. And then we use it as a foundation of our proof, and then it actually has some application. And if you're interested in, maybe I can explain later after the talk. And then the second step is something you can expect. So when we study the dimension of limit set, it's quite general to use stationary measure to approximate it, or use random walks to approximate some group actions. So we need to build the dimension theory of stationary measure for general random walks on circle. And you can expect some of the results, but for example, the exact dimensionality of stationary measures, this one is at least people expect this one holds. Yeah. And then the second is this Ledoux-Young dimension formula for stationary measures. So it means that dimension equals to the quotient of entropy. So here entropy, I mean random walk entropy, and over the exponent. So recall that for counter set, we show that, so not we show, but the counter set is well known that the Hausdorff dimension of counter set is log 2 over log 3. Log 2 is the entropy. Log 3 is the exponent. So we show a similar equation for stationary matter here. And this problem has a long history to study, and it's like, I think the dimension formula for stationary matter is one of the most important problem in the study of IFS, I guess. So our case here is a nonlinear version, but a one-dimensional version. So you can think it's like kind of conformal, but the difficulty coming from the nonlinearity. And yeah. And once we show we know how to calculate the dimension of stationary matter, we hope to use the stationary matter the dimension of stationary matter to approximate the critical exponent. Recall that the critical exponent we show that equals to dimension of the limit set. So we want to use the dimension of stationary matter to approximate dimension of to approximate the critical exponent. And this part is the key part, and we need to use combinatorics of grid group actions. And later with Jiao, so the same author, and then with Jiarun Li, with Wen Yupan, we extend this part of theory. We use a more general theory, geometric group theory, and then do the same game, prove certain variational principles for other purposes to show to calculate the Hausdorff dimension for some high dimensional fractals. So it's not a topic for this talk. Yeah. Okay. And then the last step is the most subtle step. So even though you know everything, you know the dimension equals to a critical exponent, but in general, you don't know how to calculate the critical exponent. For example, you don't know how to calculate critical exponent less than 1. And for Fraction group case, Patten-Sullivan used the Patten-Sullivan theory. Bearden used automorphic forms. They can show the dimension less than 1. But in our case, we don't have Patten-Sullivan theory. We don't have automorphic forms. So here we need to study the diametrical critical exponent very carefully, and then we finally can overcome the difficulty that lack of Patten-Sullivan theory. We use a very subtle proof by contradiction. Finally can show it. Yeah, this step is the subtle part. Yeah. So that's my talk today. Thanks.